Hello everyone and welcome to this video. Today we're going to discuss path independence, conservative fields and potential functions. So let's get started. Let's start with the definition. Now let's break this down. So let F be a vector field defined on an open region D in a space. And suppose that for any 2 points A, B in the region D, the line integral, which is integral over the curves C, f dot dr, these are vectors. Okay, this is the line integral along the path C from A to B in D is the same over all paths from A to B. And so this is basically stating that if we have A and we have B, we have this. And we have this. Also we have this. So all of these line integrals are basically the same. They have the same value. So, and for all paths from A to B, if it has the same value, if it has the same line integral, then the integral, which is this integral, is said to be path independent in D. Okay, and the field F is conservative on D. And so if you have this point, we have this line for example, and we find the line integral of this, and it turns out to be the same as this, or the same as this, or the same as this, well then this means that this integral is path independent, okay, and the field is conservative on the region D. So the region D, let's say this is our region D, okay, and these are our 2 points, and these are our 2 paths, our different paths. So we have different paths. So for any path, if we have the same line integral, then basically we say it's path independent and F is conservative. And so we have another definition here. So if F, a vector field, is defined on D, and F is equal to the gradient of F, which is, we know that the gradient is just the partial derivative of x, partial derivative of y, partial derivative of z. If it's equal to that for some scalar functions f on D, then f is called a potential function for f. F is a potential function for f. And so we might need to find the potential function sometimes. We might have some examples trying to do that. And so this leads us to the fundamental theorem of line integrals. And so let C be a smooth curve joining the point A to the point P in the plane. So this is C, this is our curve, and it joins point A and point B, and is parameterized by R of t. Okay, this is our parameterization. Now let F be a differentiable function with a continuous gradient vector f equals the gradient of f on a domain D containing C. Then this line integral is gonna equal to our potential function defined at B minus our potential function defined at A. And this is useful since we can basically easily evaluate the line integral if we know what is our potential function by substituting the values b and a in the potential function and subtracting it, and basically this would make it easier for us instead of evaluating the line integral itself. And so a vector field F is called conservative vector field if it's the gradient of some scalar function. Okay, so it's a scalar function, i.e. there exists a function f such that if the vector field is equal to the gradient of this scalar function. okay, and which is called the potential function of f. F is a potential function for f. And so we need to check whether our function f is conservative or not, and we have a way to do that. If we, for example, have f equals mi plus nj, where n and m and n are functions of x and y, then if the derivative of m with respect to y is equal to the derivative of n with respect to x, partial derivative, then the function is conservative. So here are some examples. So he's asking us to check for conservative, and so that can be easily done. So let's say first this is m and this is n. Now partial derivative of m with respect to y is equal to -1, and we have also partial derivative of n with respect to x equals to 1. So with respect to y is -1, with respect to x is 1, and they are not equal, so not conservative. Now our second example, this is m, this is n, partial derivative of m with respect to y equals 2x, partial derivative with respect to n of n with respect to x equals to 2x, and they are equal, so the function f is conservative. Excellent. Now this is m, this is n, partial derivative of m with respect to y is 2x, n with respect to x is 2x, they are equal, conservative. So that's an easy way to check whether our function is conservative or not. Partial derivative with respect to y, cosine of y, partial derivative of n with respect to x gives us cosine of y, they are equal, so f is conservative. Excellent. Now we have m, we have n, again m with respect to y. This gives us 6x squared y minus 2, and n with respect to x gives us 2xy minus 2, which is basically not conservative. Okay, so now he's asking us to find a function f such that f is equals to the gradient of f. And he wants us to use part A to evaluate this. Okay, let's use part A to evaluate this line integral. Okay, so let's go for our first example. Now we want to find f. Okay, so what function f can we find? Now this is basically, we'll need to do something like so let's take this to a new page, and I'll show you exactly how to find this, how to solve this problem. Now let's take this to a new page like this, and so we add a picture, zoom out, as you can see. Okay, so 1, we have f of xy equals 2xy to the 3i plus 3x squared y squared g. Now, in order to find f, we can do the following. So first we'll need to find partial derivative of, we need to integrate f first. So f of xy is gonna be the integral of f of xy, say with respect to x. Now this is gonna be basically 2xy to the 3. Now of course we need to substitute also the values for x and y in order to get the parameterized function. So let's get the parameterized function. Okay, so f of r of t is the parameterized function equals to, so we have also r of t equals, for our first example, of ti plus t squared plus 1 g. Now t is bigger than 0, smaller than 2 pi, and so yes, so we have cosine of t, sine, no, so yeah, our y is different. Okay, so cosine, yeah, our x is sine also, so it's 2 sine of t, and then y is t squared plus 1 all to the 3. Okay, okay, r of t, nice. Find the function f such that f equals the gradient of t. Okay, actually we can find this first. It's possible to find this first. So f of xy equals 2xy to the 3 I 3x squared y squared to the j. Now okay, so basically we have this as m of xy, n of xy, and we can do this separately, and so we'll have, for example, so this is f of xy. Okay, let's just integrate. Let's integrate the function xy to the 3i plus 3x squared y squared j. Let's start with x dx. Now if we do this, we're gonna have just x squared y to the 3 plus x to the 3 y squared, of course I and j. Okay, and then we're gonna add g of y. Now why g of y? Because if we have any function of y, it's gonna be just basically, you know, it's gonna be differentiated. If we differentiate back, it's gonna be differentiated. And so now let's do df with respect to y. It's gonna tell you y now. So f of xy, this is f of xy. But so this is the function we're trying to find this. Okay, and we have just g of y missing, so we need to find g of y. Okay, and so g of y I think can be easily found by going here and then okay, so now differentiate now with respect to y, so x squared y squared I plus 2x to the 3 y g. Okay, df with respect to y. Yep, got it. Okay, so let's tell you what happened here. Now let's delete this. Now I'll tell you exactly. I was on the right track. So basically df over dy is just 2xy to the 3. That's how we did it. So that's how we do it when we check for conservative or not. And we also have df over dx is gonna be equal just to n. equals to n, this is equal to m, and so now this should be really it. Okay, so so now f is gonna equal to f of xy, the integral of 2x to the y to the 3 with respect to y, and so this is gonna be just is it with respect to y or x? I think this is the opposite. X and y, yes. So this is gonna be 2x. And so now, yeah, so the integral with respect to x, so x squared y to the 3 plus g of y, that's what we just did. Now this is f of xy. Now in order to find really the function f of xy, we need to find g of y. How to do that? That's basically simple. So we're gonna first try to do f of partial derivative with respect to y, okay, of this function. Now this is gonna give us basically 3x squared y squared plus g prime of y, okay, so because this is a function of y, and then taking the derivative with respect to y is just gonna be the derivative of whatever that function is, and then we're gonna compare. So let's say this is, okay, let's say this is 1, this is 2, and call this 3, and this 4, and then we say compare 4 and 2, and now 2 is just 3x squared y squared, which is equal to 3x squared y squared plus g prime of y, which means that g prime of y is just 0, and now g of y is just c, which is a constant, and basically this will lead us to f of xy equals to x squared y cubed plus c. Now someone could have said, well, that's basically how we find the integral, we just add a constant. Well, it's not always the case. So in our case it was now just a constant, but sometimes it could be another function of y. It could be, for example, y squared or y squared x or xy cubed. So it's not always c, so we're gonna make sure it's that, but we're gonna always add the c, so that's true. And always add the c, but it could be more than the c, it could be also y squared, it could be other function of y, but in our example it was just c. So basically that's how we solve it. Now let's go to the part b. So he wants us to use part a to evaluate the integral of f dr, and so to do that we need to simply okay, so we need to go here. So how did we define it? Yeah, so basically, yeah, so in order to evaluate this, now we have the potential function, which is f, we found it, and now we just can easily evaluate this line integral, which is using the fundamental theorem of line integral. It's just the integral of c f dot dr is just f of b, okay, f of b minus f of a. So a is just 0 and b is pi over 2. Yeah, is that right? So now what are the points a and b? Let's double check. Okay, so the points A and B are surely not t's, so it's not like a parameter. I think it's a value that we get from the function r, and so it's basically gonna be f of b. That's our fundamental theorem of line integral, and b is gonna be basically r, so r of t minus r of t naught t1. So yeah, this b, and a is just r of t naught. Now b equals r of 2 pi, or actually pi over 2. Pi over 2, which is equals to okay, so it's gonna give us pi over 2. Sine of pi over 2 is 1i plus t squared plus 1 plus pi squared over 4 plus 1i plus 1j, and a is just r of 0, which is 0i plus 0 squared plus 1, which is j. And so the point b is just 1 pi squared over 4 plus 1, and this is just 0, 1. And now we plug in these values, so we take f of 0, 1 minus f of 1 pi squared over 4 plus 1, and this is going to give us the line integral cf dot dr. Now this cf dot dr so yeah, let's try to do this. It's just simple. So, and it's the opposite. Is it the opposite? This is the opposite. So this is b. Okay. This is b. And then it's gonna be like this, minus f of 0, 1. Now let's try to do this. That's simple. So x squared, okay, so it's 1 squared times pi squared over 4 plus 1 all to the 3. So I'm substituting in this function. Okay, so plus c is just, it's gonna cancel with the other c, and so f of 0, 1 is just gonna be 0 minus 0, and basically that's the value of our line integrals, pi over 4 plus 1 all to the 3. And that's how we find the line integral. So this could be a better alternative for us who want to find the line integral. And we can solve the second example, or I will leave it to you if you want to go through it. Now, okay, so he wants us to show that the line integral is independent of path, okay, in a simply connected domain. And so we said, in order to show that a line integral is independent, we need to show that the line integral along path c from a to b is the same over all paths from. Okay, so it's basically asking us if the function f is conservative or not. So this is the function f, and he is asking us, or this is the m. Yeah, this is the function f. Okay, this is m. This is n, and he is basically asking if this function is, if this is independent, conservative or not conservative, which is independent of path. So dm over dy equal to, yeah, so that's how, yeah, that's how basically we write. So as you can see, m dy here minus n dx, which is the same formula. So here, as you can see, So this is m and dy. So we need to check, we need to find the derivative with respect to y. So 3e, that's simple. So this is m and this is n. And then we need to find the derivative with respect to y, here to the derivative with respect to x, and then we will see if it's conservative or not conservative. So minus 2y sine of x. Okay, now dn with respect to dx is equal to 3e to the 3y, okay, minus 2y sine of x. And since these both are equal, so we could say the line integral is independent of path or conservative, full stop. And that's simple. Okay, so let's just see some regions here. As you can see, so these are some regions. Region A simply connected, region B simply connected. These are all simply connected regions since they do not intersect or cross intersect. So these are our region. So region in 3D, this is in 2D. They do not like form a loop, they're just a region. So in A and B the regions are simply connected, A and B, and in C and D the regions are not simply connected. So there are some loops. So you can see in the region, this is a whole loop, and that's basically not simply connected. So these are simply connected ones that do not have any loops or circles. Okay, but these are not simply connected. Okay, and the reason is that it can be contracted to a point inside the region containing them. So some curves inside these of regions can be contracted to a point. So this can be contracted to a point which is here. And this is the same. It's the same, and that's basically why these regions are not simply connected. So let's move on. Now, theorem 2. Conservative fields as gradient fields. So what does this mean? So let f equals mi in jpk be a vector field whose components are continuous throughout an open connected region D in space. Okay, then f is conservative if and only if f is a gradient field, okay, for a differentiable function f. So f is only conservative if there is a function, a differentiable function f, such that the gradient of it is equal to f. And so yeah, that's our theorem. Conservative fields, gradient fields f, okay, is equal to our field. And now let's see what we can do with this. So we have the function f of x, y, z, the proof of theorem 2. Okay, so this is a proof of theorem 2, as you can see. Now from A to B naught, what is B naught? This is B naught, and this is A, plus a line integral, okay, which is this L f dot dr along a line segment L parallel to the x-axis, joining B naught to be located at x, y, z. The value of f at A is just 0 here, and it goes up to B naught, up to B. Now this is our value. So example 2, find the work done by the conservative field. Now how do we find the work? So we know that the work is just the integral of the gradient dot dr. Okay, the gradient is just f. So since it's a conservative field, it's just f. Okay, and so this is basically, yeah, and he has given us the function, the potential function, and that's basically easy to evaluate since we have the points A and B, and so we know that the line integral cf dot dr is equal to f of b. Now using the fundamental theorem of line integral, now we can easily evaluate this. So this is gonna be basically, which is the work, that's what we need, okay, which is equal also to the gradient f dot dr. Okay, the work is just so f of b is just, what is b, is 1 times 6 times minus 4. Now substituting the point b into the function here, okay, so, and minus f of a is just minus 1 times the 3 times 9, so w is just like this, minus 6 times 4 minus 3 times 9 times minus 1, it's gonna be 3, and that's our work is gonna be in Newton meter. That's just basically, that's simple. So this theorem, the fundamental theorem of line integral, makes it easier to evaluate any integral and to find the work or even the flux, as we'll see now. So loop property of conservative fields. The following statements are equivalent. 1. The flux over a parameterized curve C, f dot dr, is equal to 0 around every loop. That is a closed curve C. So C is a closed curve, and around every loop is equal to 0. So if there is a loop, then the flux is gonna be equal to 0, and that's basically something we studied in the physics. You have taken physics, and also this statement is equivalent to this also. The field F is conservative on D. So if it's around every loop, the flux is 0, then the field F is conservative on D. And that's basically saying the same. So yeah, so yeah, that's basically, yeah, if the flux is 0, then this means that the field F is conservative. Okay, that's basically how we define it for the line integral. If it's the same, the line integral, then we're gonna say the function is conservative. The field is conservative F. So that's it. So if we have two paths from A to B, one of them can be reversed to make a loop. And if the reverse is 0, then the function is basically conservative. Okay, which is basically, so if the so that's very simple. So if the line integral here, line integral is equal to the line integral here, they are equal, then basically if you subtract them, so the line integral over C1 of f dr minus the line integral of C2 f dot dr is gonna be basically 0, which is basically what we have here when you subtract them. So we are reversing one of the curves, and when we add them, we're gonna get 0, and if that's true, then our field is conservative, which is basically another application of the line integral and our fundamental theorem of the line integral. So yeah, so that's basically it. So, and also the reverse is true. If A and B lie on a loop, we can reverse the path of the loop to make two paths from A to B. Okay, and there is a test for conservative fields also. So component test for conservative fields. So if we have a conservative field, which is this, or we have any field, force field, and we want to check whether it's conservative or not, so let it be a field on a connected and simply connected domain. So we are talking about connected and simply connected domains whose component functions have continuous first partial derivatives. So the component functions, so each component m, n, and p have continuous first partial derivatives. Then f is conservative if and only if partial derivative of p with respect to y is equal to partial derivative of n with respect to z. Partial derivative with respect to m, z equal to partial derivative of p over respect to x, and partial derivative of n over x equal to partial derivative of n over y. And now this is basically could look complicated if you want to memorize it like this. So one way to do it is just to put it in a matrix, and then just have this matrix, as you can see, the field F equals mi plus nj plus pk is conservative if this matrix or is this determinant. Okay, so we put it in a determinant is equal to 0, so you're gonna just do something like I j k, and then you're gonna do rho over d. Yeah, so derivative, partial derivative with respect to x, respect to y, respect to z. So m, n, and p. If this equal to 0, then f is conservative. Okay, that's basically how we do it. And we have our last definition, or a couple of definitions and some examples. Now this definition states that any expression mx yz dx ny dy bx dz is a differential form. Okay, this is a differential form, and if you talk differential equations, you're gonna see this, or you have already seen this. So, and a differential form is exact on a domain D in a space if this differentiable is equal to partial derivative of function f over dx plus partial derivative of f respect to y times dy plus partial derivative of z respect to z is equal to the partial derivative of f for some scalar function f throughout D. So if this holds true for some function f, then we're gonna say that this expression is exact. So this differentiable form is exact if we have such a function f that satisfies this condition. And so we have a component test for exactness of this form m dx plus n dy plus p dz, and the differentiable form m dz plus n dy dx is exact on a connected and simply connected domain if and only if, and we have just this, which is basically, yeah, so this is basically just doing the same I j k, and we basically, let's check. Yeah, it's basically the same. Okay, it's exactly the same. So dp dy dn dz, as you can see, these are the same thing, and if you want to check, you can just do something like d over dx, d over dy, d over dz, and then you plug in p or m and p. If this is equal to 0, then conservative. If not equal to 0, not conservative. Okay, that's basically how we do it. M and P. Okay. Now this is interesting. So he wants us to find a function f such that f is equal to the gradient okay, so this is basically the same way we did it. Just take a picture of this and try to solve it. So this is basically the same method we used for our two variable function. Now this is a three variable function. It's gonna be a bit different, but it's not very different. Okay, like this, 4x squared to the 3. So yeah. Okay, so let's do this. Let's finish our last example. Okay, so we have our function f of xy equals yi x plus z j plus yk. Now we have this is M, N, N, and P. Now we have d m over dx equal to y, d n over dy plus the x plus z, and dy over dp or dv over dz equal to y, also y. Okay, so 1, let's call them these functions 1 and 2 because we're gonna use them later. Now let's do this. So actually this is df, function df. Okay, so let's do this. Now let's integrate rate 1 with respect to x. So we're gonna have the integral of y dx, which is equal to yx plus, okay, so now let's take a look at this. So we're gonna have h of yz. Now this is gonna be a function of two variables, h, y, and z. And in order to find these variables, we're gonna need to, or these two functions, we're gonna need to do the same thing as we did before. Okay, or also we can do something like g of y plus h of z. Okay, that's our f. So we need to find both g of y and h of z. And so basically, yeah. So let's now integrate f with respect to y. So we're gonna get or differentiate x plus g prime of y. Okay, so and we call this 4. Now let's compare 4 and 2. 2 is just this. So x plus z now. X plus z is gonna equal to x plus g prime of y. Okay, I think we need to do something like this. It's better to have it, yeah, I think it's just h of yz, something like this. Okay, and then we're gonna have h of yz prime, yeah, so we're gonna have h of yz prime. Okay, and so h prime of yz is gonna equal to z, and so h of yz is gonna be z squared over y. If we integrate plus g of y. Now here, yeah, if we integrate, we're gonna get g of y. If we differentiate this with respect to z, of course, yeah, so yeah. So and now let's call this 5. Okay, so and now we want to find g of y, and that's basically, it's not hard to do. That's not hard to do. This is z squared over 2. And so, okay, so let's plug it in into our x of yz, or x of y. So we're gonna have yx plus z squared over 2 plus g of y. Now we need to find g of y, so let's just do df with respect to z. And this is gonna be xyz plus z plus, with respect to z, is just gonna be 0. Okay, it's gonna be 0. Oh, okay. So yeah, it's gonna be 0. So df with respect to z Oh, actually, we're gonna have, yeah. And this is a function of, should be a function of z. Yeah, h prime of yz. Now this is prime with respect to what? So let's specify. So h of yz with respect to, so differential with respect to z, differentiate with respect to z, it's gonna be z, then we integrate, it's gonna be g of z, yes, we're gonna be g of z, or yeah, z plus y, okay, it should be a function of xy. Well, that's weird. Let me check the answer. Just a second. Let me check the answer. Okay, so here, okay. So this is our example. This is our example, and I just basically found the function g, y, z, and that's correct. So I integrated and found the function. Now we should differentiate with respect to y. Okay. And basically he assumed y is 1. For some reason he assumed y is 1. Why is that? Let's check. Do you have it specified that y is 1? So here, yeah, so here, yeah, we had it right, So g y, okay, and then he had g with respect to y. So g with respect to y, it's just z. Okay, so we reached here. Gy yz equal to z. Okay, what else? Okay, so we got it equal to z. Now we integrate with respect to y. Okay, so when you got it with respect to z, we integrate with respect to y. Okay, so call this 5. Now we need to integrate this with respect to y. Which is basically g of yz equal yz plus g of z, h of z. Hope that's correct. Yes, h of z. So yz, h of z. Okay, and then we substituted in our f. Okay, so that's basically what I did here. Okay, let's just go here. So h of z, yes, okay. And then we put it back into our f. I just need to integrate with respect to y, not z. So put it back on our f(xy). F of xy is just yx plus yz plus h of z. Now that should be simple. So here we will have basically integrate with respect to z. Let's call this 6. Now let's integrate this with respect to z. That's yxz plus yz squared over 2 plus h prime of z. Now let's call that 7 and then compare 7 and 3, which is y. Okay, just 1 second, yeah. So is it y? Let's check, yeah, it's y. So y is going to equal yxz plus, okay, so here this should be y. I'm differentiating, not integrating. Okay, so now this makes sense. That's y plus h prime of z. Now these cancel. H prime of z equals minus yxyz. Is this true? Actually, yes. Okay. So with respect to z is just gonna be all gone, and we're gonna have h prime of z. yz, h prime of z. So yeah, yz, and then differentiate this, we get y plus h prime z. Now we compare these, okay, and we get y plus h prime of z. So basically this says that h prime of z is just 0. So h of z is just c. So finally you have f of xy, finally reach the answer, is just yx plus yz. So from here, yx plus yz plus c. And that's basically our potential function. So you need to do anything else. Okay. Okay, so he wants us to evaluate the line integral from point 214, it's point A to point B, 8, 3, minus 1. Just take this, copy or cut, go down, and let's paste. And so the line integral c of the f dot dr a3 negative 1 minus f of 2 1 4 is equal to, of course now we're gonna have 3, now let's substitute. So 3 times 8 plus 3 times negative 1, it's gonna be 5. Of course we're not gonna use the c, it's gonna cancel, and then we're gonna have 1 times 2 plus 1 times 4, which is 6, which gives us negative 1, and that's the value of our line integral. And so we can solve the rest of the examples. I'm not gonna do that. just you can check for conservative and find the potential function. If it's conservative, we can check for conservative. So this is M, N, and P. And so let's just do I, J, K. And then we have 2x minus 3 minus z cosine of z. And d with respect to x, d with respect to y, d with respect to z. 2x minus 3 minus z and cosine of z is equal to. Now, okay. So we have so this cosine of z. Perfect. Okay, so if we integrate this with respect to z, we're gonna have first 0 minus with respect to z minus 1 minus 0 minus 0 plus, so I'm just differentiating partial derivative, 0 minus 0, so we get plus 1, so not equal to 0, so not conservative. Now we could try this in B. So this is our I, and we have dx, have dy, dz, and we have, okay, so we have g, k, e to the x cosine y plus yz, okay, and that's xy minus, or xz, minus e to the x sine of y, xy plus z. That's basically, let's do this. So we have first x minus x minus y minus y plus z sine y, or z, with respect to x, so z minus e to the x sine y, okay, minus, and we go with respect to y. With respect to y, we have z minus e to the x sine y, which is basically a conservative function. This is 0, this is 0, this is 0, so this is conservative. Okay, this is conservative, which means, okay, so it's conservative. And so he asked us to find the potential function. I'm not gonna do that because it's gonna take a lot of time, but you can try to do that, and basically found whether this function is conservative or not, or this force field. Thank you for watching. We're done with this. I hope you benefited from this.